Assalamu alaikum, grade 11 students, GED 2019-2020. This is the last lesson in topic 4, electric fields. Lesson 4.3, as mentioned in your syllabus, electric potential of a point charge. Here are the objectives: to describe the electric potential energy and the changes of electric potential energy and uniform field, to define the electric potential difference between 2 points as work done per unit positive charge, to define and calculate the electric potential at a point due to a point charge, then to compare and construct electric and gravitational field. Now, before starting, let's do some revisions now due to the electric field and change in energy. Now, if we have here two parallel plates, positive and negative charged, we know that electric field is going, a uniform electric field is going to be established here between the two plates, and the direction of the electric field is from positive and toward the negative. This is the uniform electric field E. Okay, now if we have here a positive charge Q, as we know that Q will move towards the negative charge. Yes, there is an electric force acting on this Q, which is equal to E, the constant E, times the charge Q. Due to this electric force, this charge is going to accelerate. Because it is going towards the negative plate, so its velocity is going to increase. So due to the increase of the, V will increase, and what will happen, the kinetic energy will also increase. So in this case, the kinetic energy increasing and the potential energy is decreasing when the charge, the positive charge, is going with the same direction of E. And if we are having, for example, a negative charge here, so this is again positive and negative, and E, this is the direction of the uniform E. What if we placed here a negative charge? The negative charge will move towards the positive plate. Okay, so again, our F is EQ, and V will increase. Okay, again, V will here increase, but see here the charge is going in the opposite direction of E, and kinetic energy will increase, potential energy will decrease. Okay, now let's take the other case. If we want, this is the positive and this is the negative, and this is the direction for our E, uniform electric field. Now for this positive charge, we want it to go from this point towards the positive plate. What will happen here? The charge is going to repel with the positive plate. So to make it move opposite the direction of E, because a positive charge should move with the same direction of E, to make it its motion opposite to the direction of E, we have to apply a force. So that means there is an external work done. So we have to do a work for moving this charge from point to another point. That work will cause change in energy. What will happen here? Okay, it is going toward the positive plate. What the potential here, the potential energy will increase and the kinetic energy will decrease. Different in the opposite case. Because we are forcing the charge to go toward the positive plate, the potential energy will increase and the kinetic energy will decrease. Here, if for a minus or a negative charge in the same electric field, for a negative charge, the same thing, if we are going to force it to go from this point to this point, because this is the direction of the force, but if we are going to force it to move towards the negative direction, so there is a work done. And here the potential energy will increase also and the kinetic energy will decrease. So what is happening here? The work done always will cause change in energy. Okay, now here is the, for example, it's showing what we talked about. There is a stationary positive charge, for example. If you want this charge to, if you want to bring this another positive charge toward it, you have to push the positive charge. So work must be done on this charge. Yes, because there is a repulsion force between them. So to bring this charge towards the stationary positive charge, you have to do a work on the charge. So this is the case, okay, that we have the positive plate and zero potential. This means that this is negative with respect to the other plate. So let's take this positive charge. If we want it to, this is our direction of E. And we know the positive charge should be, the force on the positive charge is in the same direction of the electric field towards the negative plate. But what if we want to force the charge to move from this point to this point toward the positive charge? What will happen? That we should apply work. And what is happening to the energy here? The potential, as we said here, because it is going to decelerate when it is moving toward the positive charge, so the kinetic energy will decrease and the potential energy will increase in this case. So as the distance from A, for example, to point B, as the distance increase, the potential energy increase. So the distance is increasing and the potential energy will increase. Okay. The change in the potential energy, okay, is related to the work done. Work done is the change of potential energy, So now the work done per unit charge, the work done to take the charge from point A to point B, the work done to take the charge, for example Q, okay, from point A to point B is the potential difference between these points. It is the potential difference between point A and B. And we know that the work done is the change in energy. So let's come to a definition for the potential difference between 2 points. So the work, now if we are taking a charge from a point from the negative plate to the positive plate. So let's consider that the charge was here at point A, and we want to bring it here at point B, which is on the positive plate. So we have here, to bring the charge from here to here, we have to do work. The work per unit charge, okay, to take this charge from point A to point B will give us the potential difference between these 2 plates, or the potential between any 2 points if we are taking the charge between these 2 points. So here the work done per unit charge. We have work per unit charge. Dividing work over the charge will give us the work done per unit charge. For moving a charge from the negative plate to the positive plate, for example, from plate A to plate B, will give us the potential difference between A and B. This is the work done, this is the charge. So this is the potential difference between them, V between A and B. And this is the change in energy, work. Okay, so here we are defining the potential difference between 2 points on plate A and B. Now, what if, so this is the potential difference from the potential difference, we want to define, to come with a definition for potential. Only potential. When we talk about potential, it means we are talking about a certain point. The charge is at certain point. So, electric potential at a point, that means we have, for example, this is the direction. Of course, the lines should be parallel and inside. These are the direction for E. So for a positive charge here, if it's here, let us consider it's point A. So it means the energy at this point divided by charge will give us the potential at the same point. This is potential, which is called voltage. So here we are, okay, there we were talking about potential difference between 2 points, which was the work needed to take a charge, okay, from point to another point. And here we are talking about voltage, which is potential at a point. So it should be the energy at that point, energy per unit charge at that point. Is it clear? Now, what about units? We know that energy or work is in joule and Q is in coulomb. So this will be joule per coulomb, which is volt. Joule per coulomb. Now, is a question here. 2 horizontal metal plates, here a plate, another plate, are connected to a power supply. This is a power supply and it has 1.2 kilovolt. This means that this is the potential difference between this point and this point. Again, the potential difference here is the energy needed to take a charge from a point to another point. So it will be energy per unit charge. This is giving us the potential difference. The separation between the plates, so we have potential difference, which is 1.2 kilovolts, and we have to convert kilovolt to volt, so by multiplying it 1000 by 1000, 10 to the 3 volt. Now we have here the separation between them, 40 millimeters. So D is 40 millimeters, and divide it by 1000 or multiply it by 10 to the minus 3. This means that you are dividing it by 1000. That will convert it to meter. So the separation is 40 millimeter. The switch is then closed. When we are closing the switch, this plate will become a charge with a positive charge. This will become charged with a negative charge. So you have 2 parallel plates, conductor plates, one with positive charge, another with negative charge. It means that there is an electric field here, a uniform electric field between them. So draw the 6 field lines to represent the electric field between the metal. Okay, so to represent the electric field, okay, now this is it's starting from here, it's our first, okay, second, third, fourth, fifth, sixth, and they should be separated by equally spaces, because it is, although my diagram is not that much, because we have a uniform electric field. So you have to use your ruler to represent the lines. Somehow like this. And where is the direction? It will be from positive to negative. So this is the direction. And this is our E. Calculate the electric field strength E between the plates. So to calculate E, we have to write E. Now what we have here according to VD, so it is directly V divided by D. It will be 1.2 times 10 to the 3 divided by 4 T times 10 to the minus 3, and this is going to give us 3 times 10 to the 4. Here we have volt per meter. Okay, now let's take the graphs of potential and potential gradient. Now this is for a uniform electric field. For a uniform electric field, actually what you have E equal to V over D, and there is a minus sign here. But we were not considering the minus sign because we want only the magnitude of E. And it should be very clear here that potential is a scalar quantity, but E is a vector from positive to negative. From where this minus sign is coming? Now, if we have here again positive plate, charged plate, and a negative charged plate, we have electric field from positive to the negative. Yes, and if we have a charge here, for example a positive charge, this relationship shows us that the direction of the electric field will be in the direction of decreasing potential, the decreasing of the potential. Now, if this is plate A, for example, any point here is A, any point here is B. Now, the potential at A, the positive, is greater than the potential at B. So, potential at A is greater than the potential at B. So, where to move for getting potential, less potential, decreasing potential. So, when the charge is moved from this point, okay, to this point, it means the potential is decreasing. So it will be also the direction of E. Again, this is coming from this minus sign because the direction of E is always toward the decreasing of potential. So we know that the potential for positive and is more than the potential for negative, and closer we are to the positive, it means that we are the point has more potential than the other point which is closer to the negative. So it means that moving from positive to negative decrease the potential. This means that the direction of E will be towards the direction where the potential is decreasing. That's why this minus sign is here, but in calculations we are not using it. But for when we are dealing with the graphical representation of potential with distance, we have to consider that. Now, if we come back to the relationship here, okay, now it is the V equal to, from that relationship, minus ED here. This means that there is a V proportional to D, but in negative direction, opposite direction. Okay, so the relationship between them will be a straight line, but with negative slope. Straight line with negative slope. Now, again, this shows that the potential here, for example, here the distance is increasing, the potential is here, the distance is increasing from the positive plate, the potential is decreasing, but it will decrease in a linear, there is a linearity between potential and distance. Now, if we come to this graph and we calculate the slope or the gradient, the slope or the gradient for this line, it will be delta V over delta D with minus sign. And sorry, let's add. Now the gradient is delta V over delta D, and the gradient will be negative, so we will get here a negative sign. Going back to the relationship here, E equal to minus V over D. So you see here the gradient equal to minus V over D. So this means that the gradient equal to E. Very clear. And this is very important point here. The gradient or the slope is E, but we have to consider the minus sign. So now this means that E equal to minus V over D, and E equal to minus, this is the gradient, minus the gradient of potential. So our electric field is minus the gradient of the potential. This is the gradient. And electric field is minus the gradient of potential, because here we are going to get a negative gradient. Here we have to get a gradient in negative. Again, going back to E, we are here we have a constant slope gradient. So our E is constant, and of course it's very clear that, okay, we are in a uniform magnetic electric field, so E is constant. That means our gradient or the slope also is constant, and it's very clear here. The change in V over the change of D is constant. So if we want to represent our E with D, it should be constant. The gradient is constant for this line. Okay, what is E Here E is the minus gradient of the potential. This is E. The y-axis now is here for this graph represents, the y-axis represents E. Which is minus the gradient. It's clear from here. So it is a negative of the gradient of potential. Now here let us go for the potential energy in a radial field. Now we are talking about a point charge or a spherical charge conductor also can be dealt as a point charge, because the charge is concentrated in the center of the sphere. So for we are in radial field, so consider that we have here a point charge Q, a positive for example. So the direction, these are the electric field lines directing outside. Yes. These are the electric field lines for a positive point charge, or it is a spherical charge conductor. As we know, the charge will be concentrated here in the center, and these lines are radial this field is radial field as it is radiating from the center, or we call it spherical field. Let's come with a definition for the potential. Now, if we have also here a small point charge, which is much more less than this big charge. This is a small, and this is the big charge. Now, this is at point A. And for example, if we have, this is A and this is B, let's compare where the point which point has the greater potential. So here we have the potential, as we know, now just we mentioned that the direction of E is toward the direction of decreasing the potential. So this is the direction of E, to the left. It means when we are going from B to A, potential is decreasing. So if this is the point that has a potential of Vp, and this is the point that has a potential of Va, this means that Vb greater than Va. Closer we are to the charge that causing the field, greater potential. Going farther from the charge, potential is less. Now, if we are taking the point from A to B, for example, from A to B, it means we have, this is a positive charge, and also this is a positive charge. We have to do work. And as you know, so we have to do work, and the work done to take the charge from A to B will give us change in energy. So work done per unit charge, this charge, this is small charge which we are moving, it is energy per charge. This will give us what, as we saw before. So let's make it more clearly. It is equal to change in energy per charge. This will give us the potential difference between point A and B. Yes? Yeah, this is the potential difference. And again, we can say if we want the potential at a certain point like A, so we have to go for the energy at that point divided by the charge, and this will give us the energy per charge at that point, which is the potential at this point. So this is giving us the potential difference when we are taking the work done to take a charge from point to point per unit charge is potential difference, but the energy at a certain point per unit charge will give us the potential at that point. So till now nothing is new. And this will take us to the definition of the electric potential at a point. So it is the work done per unit charge. It means we are dividing work per total charge. To bring a small test charge from infinity to that point. Why from infinity to that point? This means we are talking about potential at certain point. Okay? Now, for example, again, going back to our, this is our charge which is causing the electric field. Okay? Now, for example, we have a certain charge, small charge here with a positive sign Q. It has a potential of A here, for example. If this charge is farther it's going, as we mentioned, less the potential is becoming. So the potential at infinity equal to 0. It is considered to be potential at infinity considered to be 0. Why? We are so far from the charge that is causing the electric field. So the potential when we are bringing a point from infinity to point A, so there is a potential difference between okay, A and infinity. It will be the work done. Yeah, it is will be the work done to bring the point from infinity to A per charge. And if the work done is the change in energy, so it is the energy of the energy here, potential energy at infinity also equal to 0. So it should be only the energy at point A divided by the charge Q. It will give us the V at point A. So see here, we started with difference, potential difference between infinity to A. Because the potential at infinity is 0, so this will give us the potential at point A. Again, in a simple way, that V infinity minus VA, this is 0, it will give us the potential at A. So we can define the potential at a certain point A as the work done per positive charge to bring a small charge from infinity to that point. And this is the relationship for a radial field. As we know that 1 over 4 pi epsilon naught is k, which is 9 times 10 to the 9. Okay, it will be in the unit of Newton meter square per coulomb square. So here, substituting that, V equal to potential at any point here, okay, that has electric field due to a radial, a point charge, a radial magnetic field, electric field. So calculating the potential at any point here within the electric radial field, it will be, we'll take this 1 over 4 pi epsilon naught in its k. So we are left with Q over R. So as you see here, greater charge we have here causing the electric field, greater potential we have. This is a potential at that point, at any point. And greater R is less potential. That's why when R is infinity, we are getting 0 potential. Now, this shows us the equipotential lines. It means all these points on the same line are separated with the same distance from the center. That's why E is the same here. Potential. We are talking about potential. Even E. Potential. They have the same potential. So also here, all points here have the same potential because they are on the same line and distance the same, have the same separation from the center. So these are equipotential lines. And closer we are getting to the charge, more potential are. So the potential here, for example, is more than the potential here. We have here a question. How much work must be done? So we are asked to calculate work. Let's write our quantities. Done by an external force in moving a charge of, this is our charge, positive charge, and 10 to the minus 6y to convert microcoulomb into coulomb. We have to multiply 10 to the minus 6. From infinity to a point. So when we are going to bring it from infinity to point, that means we are talking about a potential at that point, point A. So to point A, which is 0.4 meter from charge Q. So the distance is 0.4 meter, and this is SI unit, no need to convert, from a charge Q of 30. So this is our Q. Which Q is this? The Q is which is causing the electric field. This is the small q, and this is the big Q, which is causing the electric field. So this is the electric field source, which is 30 microcoulomb, and this should be 30 times 10 to the minus 6 coulomb. Let's draw a figure or a diagram. There is a moving charge Q. This is small q, sorry. It's also notated here, given a notation of small q. From infinity to point A, there is a charge, this big charge, capital charge, which is causing the, and it's positive, so the electric field should be outward. This is positive charge. Positive. And this is the quantity, or the quantity of the charges. And there is another small charge which is 2 microcoulomb, and we want to bring this small charge Q from infinity to this point A. And this point is at a distance of 4 from the charge 30 microcoulomb. So till the center there is 40 meters. This is 0.4, sorry. 0.4 meter. Now to calculate work, we have to apply our work equal to, here we have V equal to work over Q. Which Q? This Q that we are moving from, taking it, bringing it from infinity to that point. So Q. So that means that here W, or work, we are asked how much work, it's equal to V times Q. But where is V? We have to calculate our V first. V at this point, A, VA. We know to calculate the potential at a point due to a radial field, then we have to calculate A, V. So let's calculate V, and we are going to use K, V at A, K, Q over R, and this is the Q causing the field. So we have here 9 times 10 to the 9. This is the value of the constant, time this Q is 30 times 10 to the minus 6, and we have here R, not R square, 0.4, and this will give us 6.45 times 10 to the 5 watt V in volt. Now we can calculate the work, which is V times Q. This is small q, which we are applying work to bring it from infinity to that point. So we have to multiply 6, 4, 5 times 10 to the 5 times the value of Q2, and we converted it to coulomb, so it's 2 times 10 to the minus 6, and let's do, it will be 6.45 times 2, and it is going to give us the value of 1.29 joule. This is work, and it is change of energy, so it is joule. Yes, going, so this is the work done. And coming here to a comparison between comparison between gravitational and electric field, we have here for a gravitational field, okay, origin or mass. Any mass causes the gravitational field. Like any mass we have in the okay, in the field of gravity, so there is a gravitational field. What is causing electric field? The electric charge. Vector, okay, gravitational has only attraction. It attracted, any mass attracted to the center of the earth, for example, okay, that is the, but here for the vector force, both electric forces can be attraction or repulsion. Here for the gravitational fields, we have the F over m. Here we have the field strength, electric field strength, F over Q, as we know. Units here, we have the unit of meter per second square or Newton kg per second, and here we have the it is in Newton per coulomb or volt per meter. Okay, now these are the differences between the gravitational and the electric. This is caused by charge and this is by mass. This has the attraction and repulsion. This is only attraction. And we have here for a uniform electric field, lines should be parallel, and this is the formula we have to use for calculating it. Here G is constant. Even here E is constant, G is also constant for the gravitational field. Also we have here for the spherical gravitational field, we have here G is inversely proportional with R square. So this will give us the graph with R. Here also F and E inversely proportional with R square, but we have both charged here. And for the potential, as we have seen now, the gravitational potential V is inversely proportional to R. So this is the relationship between potential and R. As we are farther from the charge, potential will decrease. This is both for positive and negative charge, but for a negative charge, potential is always negative. For negative charge, potential is negative, and for a positive charge, potential is positive for positive charge. And here for the gravitational potential, we have Gm over R, so with a minus sign, so this is giving us the relationship between phi and R. We come to the end of the unit, electric fields. Thank you.